Okay, Assalamualaikum. Saya dah mula recording. Okay, so far macam mana you punya assignments? Anybody has started on the assignment?
Belum.
Yes. Anybody has started on the assignment?
Not yet, sir.
Yes, sir.
Yeah.
Saya dah, sir.
Yes. Make sure that you start to do the assignment so that you can send it to me and I can give some marks, the grades for the assignment.
Sir,
Okay.
sir.
Due.
Yes.
For like this
As
30.
as what I stated on the assignment sheet,
okay,
assignment 1 on the 5th of May. No.
Okay, sir.
So,
Assignment 1 30 April.
yes.
Edition ni.
So that is the date. Okay.
Oh, ada tarikh ke, sir?
So ada.
Okay.
I put the date there, and actually, if you go to the Moodle, the assignments is dated there. So when to submit and whatnot. Okay. So now,
assignment dah jawapan ke?
buat je lah dulu. Okay. So now I'm going to share the slides for lecture tonight. For tonight, basically that we are going into the next topic, which is operational amplifiers, which is in the Floyd textbook, electronic devices, corresponding to chapter 12 and 13. Okay. Okay. Everybody can hear me?
Yes, sir.
Okay.
Yes, sir.
OpAmp, basically there is the operational amplifier, okay, which is the is actually the purpose of the amplifier is that to amplify the signal. Okay? We have learned in the BJT that it can be used as amplifier. Yeah? And now we are going into the operational amplifier, which is in the IC form, in the integrated form. Can you mute your mic so that it will not interfere?
All right, sir.
Okay.
Alright, sir.
Okay. When you want to ask question, then you can switch on your mic and you can ask question. Okay. So now, now it's we start with the lecture on the operational amplifier. If you look at the symbol in the slides there, this is the symbol of operational amplifier, which is a triangle, and with two inputs, which is V plus and V minus, and you have Vs plus and Vs minus as the power supply, and you have the V out. So you have two inputs and one output, and Vs plus and Vs minus as the supply, the power supply or the biasing for the operational amplifier. And this is actually the photo of the IC of the typical operational amplifier, which is in the integrated circuit forms with 8 legs, 4 on each side. Okay. What is an amplifier? An operational amplifier, or it calls OpAmp for short, is an integrated circuit that amplifies the difference between two input voltages and produces a single output. Just like you saw just now, you see that you have V plus and V minus as the input, and you have V out as the output. So two input and one output. So it is a very high differential amplifier with high input impedance. So the input impedance is typically in a few mega ohms. So high resistance, high input resistance, and low output impedance, which is less than 100 ohms. So the main purpose is to amplify the voltage signal. So that's why it is called an amplifier. It is called operational amplifier because it can be used to perform arithmetic operation. So it can do addition, subtraction, multiplication, integration, and differentiation with the signals. You see, what you learn in mathematics now are being implemented in the electronic forms. So using the operational amplifier, you can add 2 different signals or more, 3, 4, 5 different signals. Or you can subtract the signals, or even you can multiply. You can do the integration of the signals. And you also can do the differentiation of the signals. Typical uses of this operational amplifier is to provide voltage amplitude changes, which is in terms of the differences of the amplitude and the polarity, whether it's negative or positive. It's also the oscillators, which is a circuit which provide you a sine wave, which is the oscillators, sine or cosine waves. Can do a filter, filtering circuits can filter certain frequencies, certain signals out, and many other types of instrumentation circuits. Okay, so you have different circuits, the instrumentation. Siapa tu? Mute sikit. Okay. So you can use this amplifier in various devices, in various instrumentations, right? Any questions so far? Okay.
No, sir.
No, sir.
No, sir.
Let me see. Okay. Okay. The OpAmp has 2 input signals. Okay. This, where is my cursor? The OpAmp has 2 input signals, which is the inverting input and non-inverting input. You see my cursor here that I show you. These are the input signals, the inverting and non-inverting inputs, and you have 1 output. Okay. Most of op-amps operate with 2 DC supply voltages, which is the positive power supply and the negative power supply. Okay. Op-amp basically that will not work without this power supply, because this power supply actually to provide the biasing for the transistors inside this amplifier. Within this amplifier, you have hundreds of transistors, maybe. It depends on how complex is the circuit inside. Okay?
Sir,
Yes.
saya nak tanya, kalau macam saya kata ada two DC power supply kan, so positif dengan negatif. Dia sebenarnya satu power supply dikenekkan terminal positif dengan negatif ataupun memang ada 2?
It depends. It depends. It can be 1 and it can be 2 separate power supply.
Okay.
Okay.
So basically,
normally on the circuits, on let's say for example in your handphones, you only have one battery, right? So it's actually being provided by 1 power supply.
Oh, faham.
Okay. The only thing is that you change the polarity and you use a voltage divider to reduce the voltage, for example. Let's say your battery, will give you 10 volts. But your circuit, maybe certain op-amp requires only 5 volts. Then you use a voltage divider to supply only 5 volts to the op-amp. Okay, clear. So this is actually the example of a amplifier, operational amplifier in the integrated circuit forms, where you have pin number 1, which is offset null. Inverting pin number 2 is the inverting input. Pin number 3 is non-inverting input. Pin number 4 is actually the negative power supply. Pin number 8 is not connected. Pin number 7 is the positive power supply. Pin number 6 is the output. Pin number 5 is the offset null. Right? So this is actually the configuration for the 741. 741 is the OpAmp model in an 8-pin DIL package. DIL means dual inline package. Okay, so you don't need to know what is DIL. This is just to show you an example how the what is the configuration of the IC looks like. Okay, V out will be in phase with the input at V plus. So basically that this output actually in phase with the non-inverting. So if the input is positive, the output is positive. If the input is negative, then the output is negative. So A's will always be in phase. Whereas for the inverting input, it will be 180 degrees out of phase with the input. So if the input is positive, the output will be negative. If the input is negative, the output will be positive. So this is what it means by this sentence. Then the use of V plus and V minus voltage supplies allows the output to swing in both positive and negative direction. So that's why you have this power supply plus and minus, so that you have a output swing in between minus power supply to the negative power supply. So the value will be V and minus V and V. So in between. Okay? So the amplitude will be 2V. Clear?
Yes,
Clear,
sir.
sir.
Okay. This is the internal circuitry of an OpAmp. This one is just to show you what it looks like. How many OpAmps, how many transistors that you have inside. Okay. So last lecture, we only learned about one, how to bias one transistor. So in OpAmp, you have how many? You have, let's say, start from Q1 until Q17. So about 17 transistors in this one OpAmp. So here you have the inverting input, non-inverting input, null offset. You have the output here. You have the power supply plus power supply and negative power supply. Right? So you have 1, 2, 3, 4, 5 important pin, important terminals. Inverting input, non-inverting input, output, minus terminal, minus power supply and positive power supply. So you don't need to remember this, but it's just for you to see how the complexity of the circuitry of the OpAmp. Okay. So in this OpAmp, basically that it has transistors. These are the transistors. It has resistors. So these are the resistors. You have the diodes. Okay. And also you have the coupling capacitors. These are the capacitors, the coupling capacitors. Okay. Why we don't have the inductor? Why? Anybody can answer?
Sebab kita tak nak kurangkan apa-apa.
No. No,
Sebab
because
nanti akan jadi zero.
it is actually the inductor is difficult to what do you call it? It is easier to manufacture the capacitor compared to the inductor in the circuit board. Okay. And it's easier to control the value of the capacitor compared to the inductor. Okay.
Okay, sir.
Okay. Now, when you talk about amplifier, then you have to talk about the gain of the amplifier. So op-amp basically have a gain. Basically that the input will be amplified by the factor of the gain. Let's say if the gain is 100, basically, then the input is being amplified by 100 factor to become the output value. So op-amp has a very high gain. It can be connected up in the format of in the open loop configuration or in the closed loop configuration. We will see later what's the difference between open loop and closed loop. Okay, so the gain of the amplifier typically can be in thousands, 10,000, 100,000, that kind of values. Okay, so that is an open loop gain, open loop gain of the amplifier. So in the open loop model, there is actually no feedback from the output to the input. So this is actually an example of a open loop gain, where you have the input and you have the output, and there is no connection from the output back to the input. So there is no feedback. So this is considered as an open loop model, where there is no feedback from output terminal back to the input terminal. Input denoted by a plus sign is called a non-inverting. So this is the non-inverting input. And the input denoted by the minus sign is called the inverting input. So in this example, you have two input, two different input signals. So you can see this symbol here. Basically, this is the inverting input and this is non-inverting input. So basically that the signal of this is 180 degrees out of phase between these two, right? So the amplification factor or gain AV is called an open loop voltage gain, typically in the order of 10 to the power of 5 to 10 to the power of 7. So whatever the voltage here is being amplified by 10 to the power of 5 or 10 to the power of 7 at the output. Okay, so basically that if it's 1 volt here, the input at a 1 volt, so the output will be about 100,000, something like that. It's in the order of 10 to the power of 5. Okay, clear so far? What is the open loop? Okay, with high input impedance, input resistance and low output resistance, large gain op-amp circuits can be designed to perform as ideal voltage or current amplifiers. In effect, to analyze the performance of the output of an op-amp circuit, only one assumption will be needed. That's the current flowing into the input circuit of the amplifier is 0. So basically, the input current is equal to 0. So if you look at this, basically the current going into this is equal to 0. This to the terminal plus or minus is equal to 0. Why is equal to 0? Because it's high input resistance. the input resistance is basically here, in between the plus and minus terminal. So the resistance here is high. So that's why the current is 0. There is no current flowing through this. Instead, the current is flowing this way. Right? So for the closed loop model, so
Sir,
this, yes.
saya boleh tak ulang balik sir?
Pasal tertidur ke?
Bukan, tak berapa jelas.
Which part?
Yang sebab
Open je.
yang sebab apa
Sir,
dia,
yang open loop
sebab apa
model.
dia boleh yang high tadi, yang saya cakap sebab apa dia boleh zero.
Sebab
Okay,
dia
this
high resistance.
high resistance. When high resistance, what I is equal to V over R, right?
R.
R.
Ohm's law.
Aha.
So when resistance is high, therefore the current is
Current is
approaching zero.
Zero.
Okay,
Ah,
zero.
so when it's because this op-amp is a high input resistance, therefore the current is approaching zero.
Approaching
Yes.
zero.
Zero.
Yeah. So because the input resistance is here. This is the resistance between the plus and minus terminal. So basically there is no current flowing here.
Oh, okay.
Okay.
Faham, sir.
Right? So for the closed loop model, it reduces the gains. Basically that from that 10 to the power of 5 to 10 to the power of 7, when you have a closed loop gain, a closed loop model, it reduces the gain. So it can be 10 to the power of 5 can be reduced up to maybe 500 instead of 10 to the power of 5, or reduced to 200, for example, right? So it will reduce the gain. In order to control the gain of op-amp, it must have a feedback. So you control the gain by having the feedback connection here. And this feedback is actually a negative feedback. Right? A negative feedback reduces the gain and improves many characteristics of the op-amps. So most probably that you make the op-amp is more stable, for example. Right? So this is what I mean just now. If you look at this is actually the input resistance, which is very high input resistance. Yeah, input impedance, Z in, is approaching infinity. So this is actually the ideal op-amp equivalent circuit. The ideal op-amp senses the difference between two input signals and amplifies this difference to produce an output signal. So basically that this op-amp, it senses what is the difference between the minus terminal and the plus terminal. And the difference will be amplified and presented at the output. And for the ideal one, the difference maybe is normally 0 if you have the identical input and output. So ideally, the input impedance is infinite, which means that the input current is 0. So the input current in this terminal is 0. There is no current flowing because this part is the high impedance. The output terminal of the ideal op-amp act as the output. So this is act as the output of the ideal voltage source, meaning that the small signal output impedance is 0. So basically the output impedance here is 0. Okay. So what is the properties of ideal op-amp? The properties that is infinite voltage gain, okay, infinite bandwidth, and infinite input impedance, and 0 output impedance. So sometimes in the question in the exam, I ask what are the properties of the ideal op-amp, for example, or I ask you to compare between the ideal op-amp and the practical op-amp. Okay? So this is an ideal OpAmp. Any questions so far? Any questions so far?
Sir. No, sir.
Yeah,
Sir.
no question. Okay.
Sir.
Yes.
Yep, sir.
Apa ni ideal of M ni sir. So kita guna practical ke biasanya ke guna ideal?
Practical lah. Ideal mana ada?
So maknanya ideal tak wujud dah sir.
Normally tak ada lah. There is no ideal OpAmp. It's all practical OpAmp. But ideal is actually a model.
Okay.
Okay. Now, this is the practical OpAmp. The practical OpAmp has both voltage and current limitations. So, the peak-to-peak output voltage is limited to slightly less than the two supply voltages. Basically, that's the peak-to-peak output voltage depending on the plus voltage supply and minus voltage supply. So the peak-to-peak output voltage actually in between these two values, the minus voltage supply and the positive voltage supply. Let's say, for example, that you have plus 10 volt and minus 10 volt. So therefore, the output peak-to-peak is actually in between 0 peak-to-peak to 20 peak-to-peak, because 10 minus 10 plus 10 is about, the amplitude is 20. Right? So the output current is also limited by the internal restrictions, such as the power dissipation and component rating. Because for practical OpAmp, definitely that it will generate heat because you have resistance inside, right? Remember the diagram, the equivalent circuit for the OpAmp, you have resistors, right?
Yes.
So
Yes, sir.
that resistors actually generate heat. So therefore, there are power that is dissipated as heat. So the characteristic of a practical OpAmp, basically you have a very high voltage gain, but not infinity, very high. A very high input impedance, Zin is actually very high, but not infinity, not like the ideal OpAmp. Then very low output impedance, you have some impedance, but very low, not like the ideal one, which is zero output impedance, and it's a wide bandwidth instead of infinite bandwidth. So it has limitations, right? Clear? So if you look at here, if you look at this one, okay,
Sir.
this is ideal. Ideal, Zin is infinity. Zout is 0. The gain is infinity, okay? And you compare with this, which is you have the, it's very high, but not infinity. This very low, but not 0. And you have the AV is not infinity. You have some very high value, but not infinity. And it's a wide bandwidth. Okay. That is the difference between the ideal OpAmp and the practical OpAmp. Okay. So far, any question? Clear?
Sir, yang peak to peak output voltage is limited to slightly less than the two super voltage tu maksud dia sir?
Maksud dia?
Yang peak to
Okay.
peak, apa
Okay.
beza dia?
Peak to peak. Okay. Remember this?
VPP ke sir?
This. You have minus plus V and minus V. So what is the peak to peak value?
Oh, yeah.
100.
What is the peak?
VPP.
Zero.
No. Peak to peak.
2V.
2V. Yes.
V.
That is peak to peak value.
Oh, VPP lah sir.
So if it's the, let's say this is plus 10, this is minus 10. So what is the peak to peak value?
20.
20.
Yes.
So
20.
this is what it means.
Faham.
Yeah. So peak-to-peak voltage is
Okay.
limited to slightly less than the two supply voltages. So if it's plus 10 and minus 10, so the peak-to-peak, the value of this is actually
20.
in between less
20.
than 20. Cannot be more than 20.
Okay, sir.
So
Okay.
it's
Okay,
okay.
sir.
Apa beza kalau dengan
Simple.
ideal tadi, sir?
Huh?
Apa beza
Yeah.
dengan ideal tadi?
Ideal is basically exactly
Exactly 20.
two supply voltages. Why this one is slightly less? Because you have some dissipation, some drop in the voltages, because this one is not zero. So you have some voltage drop here, right? The voltage is here, the output voltage is here. Basically, you have some resistor here, the load. So the voltage here is actually equal to the voltage input minus the voltage across this Z out. So that's why it's less than the peak-to-peak output voltage. That is less than the two supply voltages, because you have some drop, voltage drop in the amplifier. For this one, there is no drop because Z out is zero.
Oh, yes, yes.
Okay, Z out is zero. There is no voltage drop here because this is an ideal. Ideal model, you don't have power dissipated in the component of the OpAmp. Okay, clear?
Clear, sir.
Yes, sir.
Clear, sir.
Okay.
Yes, sir.
This is the OpAmp transfer characteristic. This is the transfer of the characteristic of an OpAmp. Basically, that you have three regions. The first region is the linear region. Which part is the linear region? Basically, this part is the linear region. Linear region, this is where you have your amplifier. It's the linear region. And you have the negative saturation region. This is the negative saturation region. And you have the positive saturation region. Positive saturation region, basically where the output voltage exceeds the positive power input. Here. The output is basically exceed the positive power input. And the negative saturation is where the output is actually less than the negative power input. So for the linear region, where the output voltage is linear based on the gain, where the V out is equal to the gain times V in, and is equal to the gain times V plus minus V minus. Basically, this is actually the non-inverting input terminal minus the inverting input terminal, the value of input terminal. Because VI is actually the difference between these two. So this is actually equal to the gain of open loop gain multiplied by V plus minus V minus. So this is actually the formula for the output for the OpAmp. Okay.
Okay, sir.
Any questions so far?
No, sir.
No, sir.
Sekarang kita
No,
nak
no, no, sir.
Take 5, sir.
I'm
take 5.
Take 5, sir.
Rumah pun
Take
take
5,
five.
sir.
Okay. Okay.
Siapa, sir? Siapa?
Siapa apa nak cepat habis. Cepat habis, cepat boleh siapa.
Habis, sir.
Lagi berapa slide?
Sir.
Lagi 10
Kena
je,
kata
sir.
lama ni, sir.
15.
Berapa lagi?
Habis.
What slides? What number are we now? the slides?
10, sir.
10 sir.
10.
10.
Yes, sir.
10.
Ada
10,
15.
sir.
Another 5 more,
Tengoklah.
sir.
Tengok how many that we can cover
Okay,
for
sir.
tonight.
Sir, apa beza
Yeah.
AV dengan AOL ni, sir?
AV.
Hmm.
Nanti kita tengok nanti.
Okay, sir.
AV.
Diam
AV is the voltage gain.
Boleh dengar.
Dengar gila.
AV is the voltage gain.
Oh.
And the AOL is the open loop gain.
Open loop.
Now, OL is open loop. AV is the voltage gain. Of course, it's a voltage gain because AV is equal to V out over V in. So it's the voltage gain. And this voltage gain is equivalent to the open loop gain of the amplifier. Eh? Can we continue?
Yes, sir.
Okay. Now we are going into the types of input modes for the OpAmp. The first one is that you have the single-ended input. What does it mean by single-ended input? It means that you have two inputs, right? Plus and minus, non-inverting and the inverting input, right? So single-ended input is basically that you use one for your input signal and the other one you connect to the ground. So single-ended input operation results with the input signal is connected to one input with the other input connected to the ground, just like it shows in the diagram here. This is actually a non-inverting amplifier where the input signal is connected to the positive terminal and the negative terminal is grounded. So therefore, your signal is amplified as a non-inverting amplifier. So the input signal phase is the same as the output signal phase. These are all in phase. Okay, these are all in phase. If it's positive, the output is also positive, but it's amplified. And the input negative, so the output is also negative, but also amplified. So this is actually a non-inverting. And this is the inverting, where you ground the positive terminal and the input signal is from the negative terminal. So what happened is that the positive input will result in a negative output. Okay, so the signal is actually 180 degrees out of phase. So if the input is applied to the plus input here with the minus input at the ground, the output have the same polarity as the applied input signal. However, if the input signal applied to the minus input, the output then being opposite in phase to the applied signal. So just like what I have explained just now. So this is a single-ended input. So one is ground, the other one is being used as the input. So this is the first input mode. The second input mode is that you have a double-ended input, which is differential. So basically that both the plus terminal and the negative terminal are being connected to the input signal. Okay, In double-ended differential mode, an input is applied between two input terminals. Neither input is grounded. So you see this, there is not grounded. No, both are not connected to the ground. It results to an amplified output in phase with the applied between the plus and the minus input. So the signal is in phase. If it's positive, the output is also positive, but it's amplified. If the input is negative, then the output is also negative and amplified. Okay. So this is actually a double-ended differential input. Equivalently, the double-ended differential mode can be represented by a single source connected between the two inputs. So basically, that it can be also like this. Basically, you have two different sources. One is connected to the positive, another one is connected to the negative. Therefore, the signal between these, actually, you have the VD, which is the differential voltage. So actually, this is the differential voltage. This actually representing this configuration. This can be simplified as that. So you have the difference between this. Okay. Now, another one is that you have the double-ended output. So the output that you have two output. It can also operate with opposite output. One plus and the other one is minus output. An input applied to either input will result in output from both output terminals. The output are always being opposite in the polarity. So for a single-ended input with a double-ended output, the signal applied to the plus input signal, the plus input result in two amplified output of the positive of the opposite polarity. For example, let's say you have this configuration. The input is in the positive terminal and the output is grounded. So therefore, one output gives you in phase signal and the other one is out of phase, 180 degrees out of phase signal. Okay. So this is the example of double-ended output. For a single-ended input with a single output measured between output terminal, the difference output signal is V out 1 minus V out 2. So this is the differential here. Let's say if you have this signal, this is the input signal. So the output between this, actually you have the differential signal is this. This is the output signal. The difference output is also referred to as floating signal since neither output terminal is the ground terminal. This actually is not connected to the reference. Okay. For a differential input, differential output operation, the input is applied between the two signals. When we say differential, that means that both positive terminal and negative terminal actually be connected to the input. Okay. And the output taken from the between the two output signal. So this is actually a fully differential operation where the output is actually equal to the gain of the differential gain multiplied by the differential voltage. Okay. So this is just a concept. This is actually the common mode input. This is another one, right? Which is the two signal voltage of the same phase, same frequency, same phase, frequency, and amplitude are applied to the two inputs. So when this happens, basically they should cancel out to yield an output equal to 0. So if this signal, this configuration, actually, if this if it's connected this way, you have one single input but connected to both plus terminal and negative terminal. Therefore, the output will be 0 because the differential between this is really 0, right? Betul?
Betul, sir.
Betul
Are you
ke?
sure?
Sebab dia
Sir.
dia macam ideal ke sir?
So, because like this. Because one, the positive terminal actually positive and negative. But for the negative terminal, it will be negative, positive. Dia terbalik. So when you add these two,
Yeah,
it becomes 0, right?
Yes sir.
So when this is 0, therefore 0 multiplied by the gain is always 0.
Zero.
So the output is 0. This for the ideal case. But
Ideal case, yes.
in the practical one, that it will not be 0 because there must be some differences here of the signal.
Yes.
Right?
With back.
So VD sometimes is not really 0. It has some value. So that's why it's called that you have a measure called common mode rejection. That we go through the formula after this. Its importance lies in the situation where an unwanted signal appears commonly on both OpAmp inputs. Ideally, you don't have the noise or the unwanted signal. So if this signal is clean. But in the practicality, in practical OpAmp, you have some noise riding on the signal. So therefore, because of that noise, so the voltage differential between these two terminals will not be 0 because of the unwanted signal. So this unwanted signal will not appear. So if your amplifier has a very good common mode rejection, so this unwanted signal will be eliminated from the output. Okay, but in the practical case, sometimes the unwanted signal will pass through also because this the what do you call it, because it depends on the how high is the common mode rejection ratio.
Sure.
Okay, this. What is common mode rejection ratio? It's actually the measure of an amplifier's ability to reject common mode signals. The common mode signal should be 0, right? Because the input, the positive input and the negative input, the signal, when you add together, should be 0, right? Right?
Yes sir.
But because of the unwanted signal, sometimes it's not become 0. But a good amplifier should be able to reject that. And that ability to reject is measured by common mode rejection ratio, which is called the CMRR. Is equal to the open loop gain divided by the common mode gain. So the higher the CMRR is, the better. So when it's higher, when CMRR is higher, therefore it means that this amplifier has a better performance. CMRR will be high when the open loop gain is high and the common mode gain, the ACM, is low. So you need to have as low as possible the ACM. And this expression normally expressed in decibel, in dB, or we call it dB, which is the formula is you take the 20 log of this value. That is the dB. How you convert from the absolute value to in dB. So you take the log and multiply by 20. Right? The open loop gain, AOL, is the internal gain of the device. which is the ratio of output signal over the input signal when there is no external component connected to the device. So when there is no external component except the power supply, so the open loop, that is the open loop gain, AOL. The ratio of the output signal over the input signal. Example, let's say you are given a OpAmp which has an open loop differential voltage gain of 100,000 and the common mode gain of 0.2. Calculate the CMRR and express it in decibels. So you know the CMRR is actually equal to the open loop gain divided by a CM. So therefore CMRR is equal to 100,000 divided by 0.2 is equal to 500,000, right? Right?
Yes,
Yes,
sir.
sir.
Okay. Then
Sir.
if you want to express it in decibel, you take the log of that 500,000 multiplied by 20.
Anti-lock.
So the value is at 114 dB.
Decibel.
Yes,
It's bad. And a
decibel.
bell.
Decibel.
Decibel.
Okay. So this is how you calculate the CMRR, common mode rejection ratio. So the higher the value is, the better the performance of the OpAmp. Okay. Any questions so far?
No, sir.
No, sir.
Okay. Now another parameter is called the maximum voltage output swing. Okay. This is actually, we have seen this, basically the V output peak to peak. Normally when the device is not connected to the input signal, the output of the device is ideally equal to zero volt. When there is no output, there is no when there is no input, basically there is no output, right? Right?
Yes, sir.
Uh,
Yes, sir.
so,
Yes, sir.
Yes,
so,
sir.
so this is called the quiescent output voltage. But when you apply the input, the output voltage ideal limits to peak, which is plus minus VCC. Okay. In practice, the output signal will not reach this limit, as what I mentioned before. So the V output peak to peak will vary according to the load connected to the device here. Basically, the higher the load, so the higher the V out, right? Or the lower.
Yeah. Yes, sir.
Ohm's law, V equal to
The lower.
IR.
R,
So V equal
Eh,
to
the higher.
IR. So the
Higher.
higher the load, the higher the voltage, assuming the current is constant, right? Yeah.
Yes, sir.
So that is the V out peak to peak. Other parameters, DC offset parameters, even when the input voltage is zero, there will be an output called an offset. So remember that you have the null offset pin. Null offset pin, basically that is for you to control the offset, the output offset. Because when this is happened, when there is no input, but there is some offset output. So you can use that null offset to zeroize your output. So how what are the parameters which cause for having this offset? The first one is the input offset voltage. The second one is the output offset voltage due to input offset voltage, and the total offset voltage due to the input offset voltage and input offset current. Then the fourth one is the input bias current. So those are the factors which can cause the offset value. Okay. Ideally, the offset value should be zero, but practically there will be some offset value, and this offset happens due to these four factors. input offset voltage, output offset voltage due to input offset current, total offset voltage due to input offset voltage and input offset current, and the input bias current. What is the input offset voltage? The input offset voltage is that the differential DC voltage required between the input to force the output voltage equal to 0. Basically that, what is the differential, this voltage, the VI, which requires to make sure that the output is 0. That is the input offset voltage. Here, this. What is the value here to make the VI is equal to 0 here? Okay. So the effect of this input voltage, input offset voltage on the offset, on the output can be calculated by using this formula. V out offset is equal to V input offset multiplied by R1 plus RF divided by R1. So this is the formula. Okay. Just remember the formula.
Sir,
Yes.
the formula is given ke?
For the last cohort, no formula was given.
Wow.
No formula was given for last cohort.
This given, sir.
Huh? It
This
depends. It depends on me whether I want to give the formula or not.
You very good.
Given, sir.
Huh?
Alah, saya boleh
Macam
lah.
ni,
You very good.
model ke tak faham?
Huh?
Tak ada apa, sir.
Tak faham?
Bukan, sir. Saya faham, sir.
Ya ke?
Yeah.
Kadang-kadang you cakap faham lepas
Tak,
tu.
maksud Ruzwatun tu yang saya tunjuk ni adalah contoh model ataupun
This is actually the bukan contoh model lagi. This is the model.
Yelah, masa dia ni
Model lah.
model ke, sir?
Huh? Basically that you use this formula to calculate
Ya.
the output offset.
Bila input dia connect to output lah, sir.
So this no. Basically that the input offset voltage is the differential DC voltage required. Basically, what is this value required in order to make the output is equal to 0? So with this configuration, R1, RF, RC, with this configuration, okay, R1 you know, RF you know. And if you want to make this V offset is equal to 0, then what is the V input offset? You can calculate from this. Okay, what is the voltage that you need to have here in order to make the offset voltage equal to 0?
Use the formula.
Yes, you use the formula.
So ni close loop model ke?
Of course, this is the closed loop because you have this connection. This RF
Okay,
is a
sir.
feedback.
Betul.
F is stand for feedback.
Feedback.
So RF.
Oh,
So this is the feedback resistor.
Soalan saya tadi, sir.
Huh?
Itu je soalan saya.
So this is actually the feedback. This is the
Feedback.
closed loop model. This is the closed loop model.
Yes.
So RF is the feedback resistance. Okay. So
Yes, sir.
this is actually the input offset voltage, VIO. So what is the VIO required to make the output offset is equal to 0?
Times with use the formula.
Yes, use the formula. Okay.
Okay, sir. Okay, sir.
Next. Output offset voltage due to the input offset current.
Current.
and output offset voltage will also result due to any difference in DC bias current at both inputs. So basically that you have two currents here. Basically that you have this current here to the negative terminal and the current through the positive terminal. Ideally, this current should be zero.
Yes.
Okay, but because it's a practical amplifier, so you have high, the resistance, you have very high resistance, but not infinity. So you have some small current flowing. So therefore, the offset current is actually the difference between these two current, I1 and I2. Right? So this is the offset. This should be IO, not OS. IO. So the input offset current is specified in the specification of, normally this value is given in the specification. It's given. This value is given. So the effect of the output can be calculated with this formula. So just remember this formula. It's equal to IO times RF. So V out offset due to the IO is this one. This IO times RF. Okay. So this is the formula. The next one, the next parameter is the total offset due to the input offset voltage VIO and input offset current IIO. OpAmp may have an output offset voltage due to the both factor, due to this and due to this. So the total offset voltage will be the sum of the effect of the both. This one is due to VIO. This one is, where do you get this? This value, where do you get this value?
Yang tadi sir.
Is from
V out equals
this
to
one.
I.
From this one. Okay?
VI.
Yes. You get from this one. And
Yes, sir.
this one you get from this one.
Sir,
Yes.
basically ada 3 situation lah kan sir?
4.
Oh, okay, sorry.
Okay. So this is the third one.
Alright.
So this is the fourth one.
Okay.
The input bias current. Input bias current is basically a parameter that is related to input offset current IO and the separate input bias current I plus IB and I minus IB. The separate input bias current I minus IB is equal to IB minus IIO over 2 and IB plus equal to IB plus IIO divided by 2. So the total is this. Okay? Simple. What time is it now?
10:20.
10:20. So I think I stop here.
Alright sir.
Alright sir.
Alright, sir.
The slew rate
Okay.
I will cover later.
Okay, sir.
Okay? Is it okay?
Yes,
Okay sir.
Okay, sir.
Actually, I wanted to cover.
Definitely,
Actually,
sir.
I wanted to cover the slew rate. That's actually four slides. I think I cover lah. I cover. So that next one we go through the application. Okay. So what is the slew rate? The slew rate.
Input per microsecond at which the output voltage of an off.
Can change respond to
So what does it mean?
without distortion.
So what does it mean?
Itu please explain.
It means that,
The rate.
okay, let's say you have this signal as the input, right? The step function as the input here. The step function as the input, okay? This is actually the configuration when you want to test the OpAmp for the slew rate, where you connect the input at the positive terminal, and the input, the negative terminal, you connect as a feedback. Okay, so you measure, you pump in the step function, this signal input, and you look at you measure the output. And because it's a practical amplifier, so it takes some time for the signal to rise up to the Vmax. So basically the output is from minus Vmax to plus Vmax. So it takes some time, delta T. So the slew rate is that the measure how fast that this signal can rise up to plus Vmax. So the voltage, actually, that you take the formula, the difference between this divide by the time taken. So the Vmax minus Vmax divide by delta T. That is the slew rate. Slew rate is dependent on the closed loop gain of the OpAmp. It is expressed as the slew rate is equal to the changes in the output voltage divided by the changes of time. So these changes of time is taken in the unit of microsecond, not in second, in microsecond. So that is the slew rate. Example, yes.
Ada kemungkinan ke dia akan tukar dalam second?
No, that
Alright.
is the formula which is in microsecond.
Okay.
So for example,
Okay.
the output voltage of a certain op-amp appears as shown in the figure below in response to a step unit function. Determine the slew rate. So basically that this is the given the output. The input basically a step function. The input is a step function, and this is the output basically that from minus 10 volt, it's rise up to the plus 10 volts in this function. So based on the definition that you need this in the step unit step input voltage without distortion. So basically that you take the part which has no distortion. So in this case, it's given at the part which has no distortion is from minus 9 volts to 9 volts. Plus 9. So this is actually the part that you take. And this taken, it takes about 1 microsecond. So therefore, the slew rate is basically that 9 minus minus 9 divided by 1 microsecond. So basically that 18 divided by 1.
18 microseconds.
So basically the slew rate is 18 volt per microsecond. So that is the solution.
So baru tambah ya slide ni.
Yes. I baru tambah tadi.
So tak upload lagi kat Moodle kan?
Tak.
Right.
Okay. So any question? So we are done for today.
No sir.
No,
Maybe
sir.
ada
No
later.
sir.
No question.
Maybe
Okay.
ada later.
Ada sir.
Apa benda?
Yang common, saya tak faham yang common mode rejection tu. Common mode input. Common mode input.
Rejection.
Common mode input
Yang-
apa pula? Mana?
Common mode rejection.
Bukan yang gambar Raja saya cakap plus jadi zero tu.
Plus jadi zero mana pula?
Slide 15 sir.
That yang tu sir.
Depan lagi sir.
Eh,
Lagi sir.
Lagi sir.
No sir. Slide 15 sir.
which one? 15. I don't see the numbers. So this one.
Sir dah ke belakang kena ke depan.
Ah,
Sir undur sikit. Undur lagi sikit.
yang V equals
Oh, yang plus minus jadi zero tu
Mana? This one.
Itu single, bukan single je.
that one sir.
This.
Yes.
Ah. What do you not understand?
Just plus minus minus plus equals to 0. Itu je.
Of course, because this is the signal. Let's say this is 1 volt, right? So this is minus signal. So becomes minus 1, right? Become minus 1, right?
Dah sini dulu.
What about this one?
Hmm.
This one is 1, right? Let's say,
Yeah.
so 1 minus 1,
0.
0. So 0 multiplied by the gain, the output will be
0.
0. So let's say this is a 0.5.
This one
Let's say here is 0. Minus 0.5. So this becomes plus 0.5. This one, the positive terminal become is minus
Negative.
0.5. So what is the difference? 0. 0 multiplied by the gain becomes 0. So that's why if the two signal is the same in terms of phase, frequency, and amplitude applied to these two terminals, so the common mode is actually the differential signal here is 0. So therefore, they should cancel out to yield an output equal to 0.
0.
So this is called a common mode rejection. Basically that this amplifier should be able to reject the difference signal here.
So, lebih better lah kan sir?
Basically that the higher the common mode rejection ratio is, the better is the amplifier. So it can reject the difference signal, which is not 0.
Yes.
Okay? Clear?
Yes, sir.
InsyaAllah.
Okay.
Yes, sir.
Okay. So no more question.
Maybe later, sir.
Okay.
In group.
In group. So if not, then basically you start to do your assignments. Okay. And you can submit anytime you want. But the guideline is that based on the date given in your assignment sheet. Okay.
Okay, sir.
Alright,
So any other question? If not, I will stop the recording, and after that I will upload to the YouTube, and you can view from there for your revision. Okay?
Malu masa.
Masa malu?
You.
Huh?
Ada sesi gurau je.
So okay, I'm going to
sir.
stop the recording now.
Okay, sir.
Okay.
Thank you, sir.
Thank you
Sir.
and
Thank you,
good
sir.
night. Okay.
Good night,
Thank you,
sir.
sir.
Good night,
Okay.
sir.
Thank you sir.
Welcome. Bye.